All right, so now we are back, and sorry about the phone interruption and all that. Hopefully, this is going to work just fine now. Let me see what color. Let's go blue. All right, so you can see on the next page the sigma notation theorems. Make sure that you know those. You need to have those memorized. The sigma of a constant is that constant times n, the upper limit. So for example, if you had and notice that this is starting with I equals 1. All of these formulas have to start with I equals 1 in order to work. And this is going to go to some number. So let's make up a number like 5 of the constant 3. And that's simply going to be the constant 3 times 5, of course, which is 15. The second one, sigma I, is another formula that you'll need to know. Let's give you a quick example of that. So if we had sigma I equals 1 to 6 of I, then according to this formula, you should get 6 times 6 plus 1 divided by 2, which is 21. So you can see that these are just simply substitutions. Make sure that your lower limit is 1. And if it's I squared, for example, you'll just substitute in n, whatever the upper bound is, into that formula. So let's do that with 6 again. So if this is I squared, this will become 6 times 6 plus 1 times 2 times 6 plus 1, all divided by 6. And so 7 times 13, 91 is what that should be. All right. So if we want to evaluate, let me move this down a little bit. Just a second. Move this down so you can just kind of start anew. All right, so the next example asks us to evaluate sigma I equals 1 to n. The formula is I plus 1 divided by n squared. For n equals a bunch of various values. So what we're going to do before we try to do any substitutions, particularly since there are 4 of them to do, is we're going to simplify this as much as we can. So that n squared that's in the denominator, I'm going to pull that out in front. And again, I can do that because since the variable of sigma, its index is I, any other variable is considered to be constant. And so n squared is a constant. Since it's in the denominator, you pull it out, and it's 1 over n squared times the formula I plus 1. Now, if we use the property of, if you have a sum, you can split that into 2 sigmas, then this would become sigma of I plus sigma of 1, a constant. So according to the formula, the theorem 4.2, one of those is that sigma I is going to be whatever the upper bound is n in this case. We used some numerical examples earlier, but with n, that'll be n times n plus 1 all over 2, plus And this is the sigma of a constant, and so it's that constant times the upper bound, which is n. Okay, so now that we've gotten that accomplished, we can do a little bit of algebra and simplify this a bit. This is n squared plus n over 2. And that's n, and in order to do the addition, I'm going to get a common denominator by multiplying this by 2 over 2, so it will become 2n over 2. And then we can add the numerators because we have the same denominator, so that's going to be n squared plus 3n all over 2. And again, let me move this down a bit so that we can see more. You can tell I'm getting used to this, so I appreciate your patience and your bearing with me here as I make a few mistakes as we go, probably. Okay, now moving it up. Okay. Then we can multiply 1 over n squared times this. And what I'm going to do that multiplication is I'm going to factor out the common factor of n in the fraction that's inside of the brackets. And one of the n's in the denominator cancels that n in the numerator, leaving n plus 3 over 2 times the other n. Okay. Now, what we could do is just substitute the numbers 10, 100, 1,000, and 10,000 into this formula and very quickly find our 4 answers. For 10, it's 0.65. I guess I can record these. For 100, the answer is 0.515. For 1,000, the answer is 0.5015. And for 10,000, the answer is 0.50015. And so if you think about it, as n goes to infinity, does this seem to be approaching a limit? We talked about limits earlier. So could we say that the limit as n approaches infinity of this sigma problem that we've been dealing with, which is sigma I equals 1 to n of I plus 1 over n squared. What would you guess that that is? I'm assuming that you're seeing what I'm seeing and that this approaches 0.5. Now, this is probably not the best way to do a problem, is to simplify it and then substitute in 3, 4, 5 different bigger and bigger numbers to guess that. So you can probably assume that we're going to encounter a faster way to do this, as we've seen some other things. We found the slow way and then maybe a speeded up way to do it. But for right now, this is a guess that our limit is 0.5. Now, if you read the next thing about area, we can see that the area of a rectangle is used to find other areas. For example, you can see how a triangle is actually half of the area of the rectangle. If you took the part of the triangle that's in the left side, if you flipped it over, it would be the white portion. And the other one where it's H and B are the legs, flip that over and that would be the white portion. So that triangle is exactly half of the area of the rectangle, so 1/2 base times height. Then you can then take that to polygons, and once you know how to do the area of a triangle, a parallelogram, for example, is basically two triangles when you draw that diagonal. So you can find the area of the two separate triangles and add them together. A hexagon, you could find the area of those 6 triangles and add them all together. And just a random polygon, add the areas of those 3 triangles together. Find the areas of regions other than polygons was something that the Greeks really wanted to find, and they wanted to be more accurate. So what they did was they did something called the exhaustion method. The clearest description of this was given by Archimedes. So basically, we take a limiting process and we squeeze the region that we're trying to find the area for between 2 polygons. So for example, you have in the next page, the circle that's got a hexagon inside it, an inscribed hexagon, and you can find the area of that, and the circumscribed hexagon and find the area of it. And of course, the area of the circle is between those 2 areas you found of those circumscribed and inscribed hexagons. You can make more sides to your polygons, and notice when you go to n equals 12, you look at that picture, the difference between the inscribed area and the circumscribed area is not that great, and so we're honing in on the actual area of that circle as n goes to infinity. So now let's look at example 3. If you look at the picture that's provided, we want to find the area under f of x equals negative x squared plus 5 between the x values, x equals 0 and x equals 2. So that's the curve drawn, and the 2 approximations that we're asked to find, one where all of the rectangles are inscribed versus where they're all circumscribed. And so the right-hand endpoints of the 5 intervals are each are 2/5 I. Lost my cursor. Oh, there we go. So the right-hand endpoints of the 5 intervals are 2/5 I, where I is, oops, where I is equal to 1, 2, 3, 4, and 5. So for example, for the second rectangle, the right-hand side is 2/5 times 2, 4/5. If you look at the picture, the right-hand side of the second rectangle occurs at x equals 4/5, as I just said. So this would be the right-hand side. The width of each rectangle, which we're going to call delta x, is 2/5. How we can arrive at that, by the way, is that the width is delta x is 2/5. That comes from taking the right-hand side, x equals 2, which is going to be represented by the letter b, and you subtract from that the x equals 0 value. Generically, we call that a, and divide that by the number of rectangles. So the right side x value minus the left side x value of the region divided by n separates the width of the region b minus a into n equally spaced rectangles. So in this case, I got that from taking 2 minus 0 and dividing it by 5, the number of rectangles. That's where the 2/5 came from. So what we could do then is we could take the area of each rectangle, calculate it, and add those up. So the width is 2/5, and the length of that rectangle is a y value. Because we're going from the x-axis to a point on the curve. In this case, that curve is coming in and touching our rectangle on the right side at that place. So this is going to be our function value evaluated at the specific x that creates that y value right here. And so I'm going to call that generically x sub I, where I is the number of the rectangle. And so, so for the first rectangle, the right-hand side is going to be, well, excuse me, let me back up. We're going to do width, which is 2/5, times the length of the rectangle, which is f of x sub 1 for the first rectangle. And if you look at the first right-hand side, where we're using x equals 1 first, 2/5 times 1 is 2/5. So this will be 2/5 times f of x sub 1. Oops, excuse me, I just said that. Back up a second. F of 2/5. So the first rectangle's right-hand value for x is 2/5. And so this is going to give us the area of that very first rectangle. So if we do that in a more generic way for all of the rectangles, we're going to be wanting to add up. This is why we do that sigma notation. From I equals 1 from the first rectangle to 5 through the fifth rectangle, we're going to be finding f of 2I divided by 5. That's that 2/5 I that I mentioned earlier, which gives us the x value of the right side of each of those, multiplied by the width, 2/5. So what we're encountering here is something that we can actually find a value of using our properties of sigma and our theorem 4.2 results that we got earlier. So let me continue this right here. So this will be sigma from I equals 1 to 5. And our function was the opposite of x, which is 2I over 5, quantity squared, plus 5. So that's the f of 2I over 5, multiplied by 2/5. And to calculate that, we'd pull that constant 2/5 out in front. Then doing a bit of algebra, that will end up simplifying to be the opposite of 4I squared over 5 plus 5. And then I can split that into two things because we have a sum. So sigma of the first formula, which is the opposite of 4/5 times I squared, plus sigma of the constant 5. So if I then use the property of how to deal with a constant again, I can pull that negative 4/5 out of the first sigma, leaving I squared inside, for which we have a formula, plus, and now the second one, I think I'm ready to go ahead and evaluate that because this is sigma of a constant, and we've already seen that that's that constant times n, the upper bound, which is 5 in this case. So now we've got 2/5 times negative 4/5 times, now the I squared formula, if you recall, has us taking the n, which in this case is the 5 that's on top of the sigma, it's that upper bound, and that's our n. So if we apply that to this problem, we're going to have 5, the upper bound, which is n, times 5 plus 1, times 2 times 5 plus 1, all over 6, plus, and then 5 times 5 simplifies to be 25. And if you do all of that arithmetic on your calculator or by hand, if you don't have a calculator, you'll get 162 over 25. So that is our estimate of the area, and since in this picture this was the first one where they were inscribed, that area is actually too small. Okay, so our actual area for this region is going to be bigger than this result. Okay, looks like I've run out of space on this sheet, so I'm going to stop for now and I'll come back with the next segment.